So guys, let's start. I'll start with something very simple. Let's say we had talked last time about one simple thing that uh, computers have memory. All right, and we had talked about what units the memory is measured. So if you remember, so a memory inside a computer system is just the smallest unit is called as a bit. All right, and consider a bit as a block of memory which can store only two values, 0 and 1. All right, and this is the smallest chunk available in computer systems. There's nothing smaller than that. All right, it can be either 0 or 1, but why do we have 0 and 1 over there? Why do we call it like that? Any idea? Anyone? No? All right. So consider something like this. Let's say you have a light bulb. All right. Cool. Now this bulb can be either in on state or off state. Cool. Why? Because it's a powered device. Same way what computers do is computers, the memory that you have, consider it like a switch. All right. The switch can be either on or it can be off. So if it is off, it is considered as 0. And if it is on, or if it has some power inside it, it's considered as 1. So what computer system do is they use this on off or whether power is there or not to represent information. Cool. But a bit can represent only two symbols, like it can be off or it can be on. So off can be called as 0 and on can be called as 1. All right, it's up to us what we want to choose, but typically this is the notion, like you call 0 as off and 1 as on. And you can a bit can be either in on state, it can have 0 or it can have 1, it cannot be both. Cool. But if you have one single bit, so what I can say is uh, so this 0 and 1, these are notions of humans. All right, we follow a number system which is called as decimal number system, where we have numbers like 1, 2, 3, 4, 5 till 9, and using these numbers we are able to represent any kind of numeric value. And we also have two symbols, plus and minus, to denote whether the number is positive or negative, and this is called as decimal number system. Cool. Now what happens is, so for this on and off, we have given a notion of whether it is 0 or 1. All right. So if I just have one single bit, I can say if the value or the bit is on, or let's say when it is off, I'll consider it as the decimal value of 0. And when the bit contains or when the bit is on, in that case, I will call it as the decimal value of 1, this thing. Cool. But now if I want to store the remaining values inside the computer system, it's not possible to do that with just a single bit. Instead, what we do is, if we take 2 bits at a time, all right, now there can be 4 situations for these bits. One can be both are 0, one can be this is 0 and this is 1. Then it can be 1 and 0, and it can be like both the bits are on or both are 1, 1. What we do is, now we can say that we will call this as 0, we'll call this as 1, we'll call this as 2, and we'll call this combination as 3. Now I'm able to represent how many different cases? I'm able to represent 4 different values from our number system. If I increase the number of bits to 3, then the number of values will also increase. It will become like 2 to the power 3 equal to, you can represent 8 different combinations. This will be 2 to the power 4, that is you can represent, 2 to the power 2, that is you can represent 4 combinations. All right, so that depends on the number of bits. So if I take a value of 2 to the power 3, it means I can represent values from 0, 1 till 7, because we are including 0 also. So this is the idea about your computer systems, that they represent everything in the form of bit. And then comes the notion of your byte. All right. So in case of a byte, what a byte is a collection of 8 bits. All right. I think most of you guys would remember probably from school or maybe college, depends. And this is roughly equivalent to 2 to the power 8 combinations, equal to 256 different values you can represent inside a single byte. So if you have 1 byte of memory, you would typically say that it can contain values, different values, which can be represented as 256. Cool. Now, if I take 2 bytes, the number of different combinations would become 2 to the power 16, which would be roughly equal to 65,000, some number is there, 65K something. I don't remember the exact value. But roughly around that many values you can represent. So as you keep increasing the number of bits inside that you are using, or the number of bytes that you're using to store data, you can represent different kind of values or different range of values for that can be stored inside the computer system. Is this part clear? Rough idea about how memory is, as the number of bits or as the size of memory changes, the amount of data that you can represent in terms of numbers or in terms of numeric values, that changes based on that. That clear, guys, everyone? Let me know if you have any doubts here. Now, this thing is called as, so there is a notion of number systems in programming languages. All right. So coming to that part. So if we talk about number systems, so there is one is binary. Binary means 2, so this has only 2 symbols, which is 0 and 1. We have decimal, which we always use, which is having 10 symbols, which is from 0, 1, 2 till 9. Then there are other 2 systems also. One is called as let's say hexadecimal, which has around 16 symbols. And for those 16 symbols, it would do something like this: 1, 2 till 9. And after 9, it uses A, B, C, D, E, and F. It uses 6 alphabets to represent the remaining 6 values, which cannot be, for which we don't have a numeric number or a symbol, numeric symbol. All right. Then there is another system called as octal, which has 8 different symbols and which contains 1, 2 till 7. This is roughly the same thing as this thing. So if we take a combination of 3 bits, all right, so we were getting 8 different combinations, and we were able to represent only 8 different values, which was 0 to 7. So roughly octal is that kind of representation, which each symbol would require 3 bits to be encoded. All right. Now coming back to this thing, so this is the number system which is native to the computers. All right, this is what computers do. This is what we use, and this is used sometimes for representing bigger values inside computer systems. All right. Why this happens is because if you look at this thing, there are 16 different combinations over here, and 16 different combinations means it's 2 to the power 4 equal to 16. So what happens is, sometimes if you have to represent the value that is stored inside a single byte, what you do is you can represent it with 2 hexadecimal systems. 2 hexadecimal characters. For example, if someone writes FF, this is equivalent to writing 256 inside decimal number system. All right, 256, or I think it should be 255, because the values start from 0 and then they go till 255. So if someone writes FF, so it's equivalent to writing 255. And if people used to write assembly kind of language, code in assembly language, not in high level languages, they would write something like this. I have written this too. All right. So this number system is also used, but typically computers internally use binary. We use decimal, and sometimes we also use hexadecimal to represent certain kind of things. All right. You may find hexadecimal kind of things written sometime in code. So this is a rough notion of how memory is structured. So 1 byte is, if we split it into 4 bytes, that exactly fits 2 hexadecimal characters. And 1 byte can represent maximum of these many different symbols, 0 to 255. So I think this should be clear. Now the thing is, why does this all come into picture? Why do we have all these different combinations? And also one more thing is there, you can convert from one number system to another. For example, if a value is in binary, you can convert it to decimal, you can convert it to hexadecimal, you can convert it to octal as well. And you can do the reverse also. You can convert from decimal to binary. There is a way to do that. It's very simple. But there is a way. I am not going to explain the way right now, but it's simply, if I write value something like let's say 8, so the binary equivalent of 8 would be there is a shorter way of writing it. All right, so this would be the binary equivalent of the value 8. Cool. So we can convert different values from one number system into another. And for binary, I'll explain you how that happens because you might need that at some point of time. Cool. But for the other ones, it's not needed. So we can skip those. For binary, I'll explain that to you. Cool. So this is somewhat about memory and somewhat about number systems. In terms of memory, coming back, we also have, I think everyone would be aware, there is 1 kilobyte or KB, there is 1 MB, and there is 1 GB. Would anyone like to tell me the relation of these things with respect to a byte? Anyone, guys? How do these convert to from a byte, or what is the relation? It's just like you have a meter, and in meter there are 100 centimeter or 1000 millimeters. Like that same way, we have this notion of kilobytes, megabytes, and gigabytes, and then terabytes, and then there is a lot more. So 1 KB is 1024 bytes, 1 MB is 1024 KB, and 1 GB is 1024 MB, and 1 TB is 1024 GB. And why is this 1024? Because 2 to the power 10 is equal to 1024. All right. That's why this is this number. It's not 1000, it's 1024. Because 2 to the power 10 is equal to 1024. And everything runs in the form of 2 or in powers of 2 in computers. Why? Because in a binary system, there are only 2 symbols. And as you increase the number of bits, the number of combinations is roughly equal to 2 to the power n, where n is the number of bits. Cool. So that's the reason why everything comes in powers of 2 in computer systems, because everything is dealt in terms of binary. Since you have 2 symbols, the number of bits you have, the more number of symbols you'll be able to represent over there. Cool. And there are some other powers of 2 which typically every programmer remembers, which is 512. 512 means 2 to the power 9, then there is 256, then the half of it is how much, 128, then there is 64, then there is 32, then 8, then 16, then 4, then 2, and then 1. So if you would see, your hard drives or things are also often in these sizes only. Cool. 128, 256, 512, like that. There is a reason for that because of all this stuff. Okay. So that's the rough idea about the memory and all that. Now coming to the number system, let's say I want to store some data inside my computer. All right. Let's say my data contains a number. Let's say I'm going to store some person's, let's say, salary. Let's say the salary is 70 something something, or maybe I'm taking this specific number because it fits into a range of integer values. All right. So if I have to store, let's say, this particular number inside my computer system, I'll need to take up some memory. Now the thing is, how do I decide how much memory is needed and what standards do the system follow for all that? So for that, what I'll do is I'll show you one quick thing. We'll talk in terms of other programming languages for the different data types and the sizes, because in Python, things are somewhat different. We'll discuss about it. Let's go to probably any website should work. Till the time they give us a table like this. Yeah, this is what I'm interested in. So when you're storing data inside a computer system, you can have 2 kinds of data, as I would see broadly. One is like numeric data and one is like non-numeric data. All right. When I say numeric data, numeric means again 2 kind of data. Numeric can be a number, an integer, let's say -1, 0, +1, 200, or any kind of number. Then there can be numbers with decimals, -1.9999 something, or any kind of decimal value, 0001. It can be positive or negative, it doesn't matter. So this kind of values are called as integers, or in short, they are denoted as ints in most programming languages, and these are called as floats. the fractional values or the one with decimals are called as floats. And then there is another kind of thing. For example, I can store numbers pretty easily with this thing. All right, but if I have to store my name, all right, let's say I have to put my name. So my name is not a number. Okay. And in case of names, we have to store each and every symbol separately over there. So for these things, typically programming languages have a special thing called as character or char data type. All right. And the idea is, if you look at this particular number 200, you can convert this number 200 into binary. All right. Because how the conversions happen is they happen by multiplying or dividing by 2, depending on what operation you are doing. And once you do that, since you're multiplying and dividing things, so you can convert a number or you can divide or multiply a number. But can you multiply an alphabet with a number or divide it by a number? It's not possible. So for storing these kind of things, the system has to do a special kind of encoding and decoding. We'll talk about that. So if I come back to this thing over here, you will find that they have mentioned roughly if I have to look broadly, there is a character data type, there is an integer data type, and then there is a float data type. All right, all other things are variations of that. And if you look at it, it says char data type takes 1 byte. And when we say 1 byte, you will notice that the range they have specified is what I've already told you, 0 to 255, because it's a 1 byte. Now what happens is, when you're storing values inside inside a byte, all right, the idea is you can use that byte to represent only positive values, or you can tell that I want to represent both positive and negative values. But when you say I want to represent both positive and negative values, then the range of values changes. All right, and there are certain more notions about that. Let me show you quick. So what happens in case of values is, so what system does is, we'll talk in terms of 1 byte. The same logic will apply for let's say 2 bytes or 4 bytes, like that also. Let's say I have a byte. Cool. And this is a byte, so there are how many bits? 1, 2, 3, 4, 5, 6, 7, 8. 8 bits are there. So what they do is, there is a notion called as most significant bit, MSB, or most significant bit, and there is a notion of LSB. LSB means least significant bit. Why it is called as, there is a reason for that. We'll talk about it. But what they do is, they say that if you are going to store both positive and negative values, you are going to reserve the most significant bit for storing the sign. And you can say if the value is 0, the sign is positive. If the value is negative, then you would put a 1, or vice versa. It depends on how the system is storing the data. But there is a predefined notion that if the value is 0, it will be positive or negative, and if the value is 1, it will be negative or positive. It depends how you are building the thing. All right, now what happens is, since you have reserved 1 byte or 1 bit, sorry, 1 bit, or the first bit or the most significant bit of your byte for storing just the sign of the value, the range of values becomes half, or it gets reduced to half. Because if the total range was 256, you can store 256 symbols, which is equal to 2 to the power 8. All right, after using 1 bit for sign, you are left with 2 to the power 7, which is equal to half of it, obviously, which is 128 different values can be represented. Now what happens is, since this range has to be split in both positive and negative sides, so you have a range which starts from minus 128 and goes to plus 127. Why it is not 128 over here? Because in the middle there is a 0 also. So to account for 0 such that you have total of 256 values, so negative range will always be 1 more than the positive range. So if you look over here, they have a slight mistake over here. It should be 128. All right, it shouldn't be 127. And the total range is still 0 to 255. So if you are going to put both positive and negative values over there, it's going to be like this. If you put only positive values, it's like this. But the char kind of data type is used to store symbols. It's not actually used to store numbers. All right, but in a computer you can only store binary data, which can be generated only for numeric values or number values. So what computers or what systems do is, they have a notion of encoding. And the one thing you might have, maybe I think might have heard, is Unicode. And you might have seen maybe UTF 8. If you have ever saved a text file, it might have asked you what kind of encoding do you want. All right. So there are different encodings, and there is another encoding which we'll talk about right now, which is ASCII. All right. So what these encodings do is, since I cannot store an alphabet, let's say there is an alphabet A, can I store it, or can I divide it or multiply it by some number? No. So how do I store it in by converting it to binary? So what this is, that for each and every symbol, you keep a mapping that this value maps to 65. They have a predefined value, and this is the ASCII mapping. ASCII mapping says that for capital A, the corresponding numeric value is 65, or if you have a numeric value 65, it can be converted to the alphabet A. Now, can you convert the 65 to binary? Yes. Can you store it inside a computer? Yes. All right. Now, for capital B, it would be 1 plus 65, which is 66. Like that, it keeps on going till capital C. Then comes small alphabets. So for small alphabets, typically you would think that the ASCII value or the numeric value would be smaller. But the thing is, they are actually larger than the corresponding capital ones. So small A starts from 97, and then small b is obviously 98, and like that it keeps on going. So these are the mappings. There are other mappings for numbers also. I'll show you how to do that in Python right now. So we'll do a bit of Python also, but this is the idea. So what computers do is, they, whenever you type a piece of text and say I want to say my name, so what it would do is, it would convert each and every symbol to the corresponding numeric value, and then convert it to binary, and then dump into your system. Similarly, when you print it, it would actually load the binary value. It will be converted to this kind of the numeric value which is there. And then from that, the corresponding symbol would be picked up, and it would be displayed or printed on your screen. That's how computer systems work. So when you're working with textual data, it is actually encoded and decoded by the system when you are reading or writing it. And there are different encodings. So ASCII encoding uses 1 byte to store the data. All right. Whereas Unicode uses a 1 to I think 4 bytes. It's not fixed. So when I say to encode data for each symbol, it will take 1 to 4 bytes. It's not fixed. It depends on what kind of system it is, because your ASCII encoding can represent only the alphabets of the English language. All right. And some numeric values and some symbols like greater than, less than, equal to, comma, full stop, etc. But your Unicode encoding supports many languages. All right. And that's why most of your, like, Unicode is what your browsers, etc. also use, because they have to be rendering things in different kind of languages, not just English. So the encoding that is used for most of the places nowadays is Unicode encoding. And in Python, remember one thing, everything is Unicode by default. In certain programming languages, for example, I had shown you this example of C++, where I was telling you about the data types. But if you come to Python, Python always uses Unicode by default. This programming language, C and C++ kind of languages, they used to use a character or ASCII kind of encoding by default. All right. So over there, you had to worry about it, but in Python, you don't have to worry about all that. All right. So in Python, you don't worry about it. It will automatically deal with Unicode. You don't have to do anything over there. All right. So this is some idea about the three things. One is integer values. One is float. Float are stored in a special way. I'll talk about it, but one is integer. Integer is the simplest one to understand. Then there is float, and then there is text or character or string kind of thing. And this is also called a string or str. So this kind of information, which is textual in nature, is called as strings in programming languages. And normally in Python, it is called as str in a short way, just like integers is called as int, float is float, but strings are represented as str in terms of Python. All right. Now, this is a rough notion of how storage will happen when you dump anything inside your computer system. Even when you are writing code, for example, if you type anything in a Python interpreter, or when you save any kind of code also, that code is text that humans can read. So that code gets stored in the form of this thing, your, what I should say, in the form of after encoding or after converting it to, sorry, after decoding the text from the corresponding encoding to binary, then it gets stored on your system. It always happens like that. All right, I thought I had uninstalled Python. All right, this thing is working. So I'll show you some examples soon. But is this clear? Any kind of questions or doubts you have, guys, at this point? No? Okay. Are you guys getting this thing? If you want me to explain something specific, do let me know. All right. So now I'll come to a bit of conversion. All right, I'm just explaining it to you. If you just search on Google conversion from binary to decimal, decimal to hexadecimal, all that, you'll get all kind of content. But to give you an idea about certain things, so we are going to talk about decimal to binary conversion first. So how that happens is, let's say I have a number which is, let's say, 23. What you do is you divide it by 2. All right, so this is 1. 1. All right, so if I divide by 2, so I can divide it by 11. So you don't have to go into the decimal part. So what you do is you divide it by 2. Whatever comes, you put the remainder on the side. All right, so if you divide it by 2, there is a remainder of 1 because this is an odd number. Then you divide it by 2 again, you get a what over here? The quotient you write over here, which is 5, and the remainder you write over here. Then you have with 2 again, you divide it by 2, you get a 1 over here. Then you divide it by 2 again, and you get the quotient as 1 and the remainder is what? 0. All right. Now, whatever number remains at the end, you can write it as it is. There is nothing to be done over here. And if you read these numbers or these remainders from bottom to top, that would become the binary representation of this particular value. And the how you write it in text is like this. You write this base. So this is called as base. So this number is in base 2 or in binary number system, and this number is in base 10 or decimal number system. All right. So this is the way things are written, and the representation of 23 in binary would be something like this. You just keep on dividing, and then you get this thing. If you have to do the opposite, all right, you have to convert from binary to decimal, then the logic is very simple. So what you do is you take the binary representation. Let's keep some spacing over here. And you start multiplying it by 2 to the power something, 2 to the power something, 2 to the power something, 2 to the power something. And you add all of these. What powers you put is you start from here 0, 1, 2, 3, and 4. So 2 to the power 0, anything to the power 0 is 1. So 1 into 1 gives you 1. Plus this would give you 2. Plus this is 4. Plus, since this is 0, it will be 0. We can ignore that. And this is what? 16. Now, if you add all these values, you will get 23 back. So this is how you can convert a value from decimal number system to binary and binary to decimal. So it's just a multiplication and division and addition, arithmetic operations. And this is for binary number system. There are ways to convert, like when you convert from one number system to another, you have to do similar things from hexa to binary or binary to hexa, or from decimal to hexa and all that stuff. But essentially it's a numerical or mathematical operation. All right. For if you ever look at a binary value, all right, let's say I write 1 1 1 2, not 2. 2 is not a valid symbol for binary. Let's say this. So if you have to convert it to decimal, a very simple thing we learn when in school or college is like you just write it like this: 1 2 4 8 16 and 32. You just put powers of 2 and you just add them wherever there is a non-zero thing, you just add them. So this is 0, ignore. 2 plus 8 10, 10 plus 16 26, 26 plus 32 gives you 58. So this is the binary, this is the decimal equivalent of this binary value. All right. This is how typically people would convert, and it is sometimes needed in programming languages like encoding from binary or converting something to binary. Sometimes you might need to use it. So this is the rough idea. Same if you want to break down some decimal number, let's say 40, into a binary, you can consider it something like what is the closest power of 2 which is just less than 40? It is 32, because after 32 you get 64. So you write 1 over here. All right, then can you add 16 to 32 and get 40? No. Then can you add 8 to 32 and get 40? Yes. So you put a 0 for 16, you put a 1 for 8, and then you don't need to use 4, 2, and 1. So you put a 0 0 0 over there. So this is how typically quickly people do these conversions it might be rarely useful for you, but you should have an idea like this thing exists in the world and how things work. This is taught in computer science. All right. So how many of you remembered this thing or are aware of this thing, all this stuff? Uh, Do you remember, guys?
Yeah, up to some extent. I've forgotten a bit.
All right. I think you would have forgotten a bit, but this is important to, in some cases, not always. Yeah. What about you, Chinna? I think you are the only one who is not from some programming background.
Yeah, it's
Do you
like,
got this thing?
yes. It's like going back to maths class.
Yeah, so this is something that would be taught in one semester, not entire this thing only, but it's usually taught in colleges. A revision is done after school.
Yeah,
So
but it's
anyways,
very
this is
nice.
how
Very well explained. Thank you. It's very clear. Yeah,
thanks to my teacher, he explained me this way.
that's great.
Yeah, so cool. So this is how actually your systems are going to store things and do things behind the scenes. All right. Now, if you would notice that if I look at this number, this particular thing, the one which I just converted 58 thing, if I just drop this bit, let's say this bit is lost. So what does this value become? It would become 56. All right. There is a loss of data, but the change in the value is not that much. But if I remove this bit 32, the value would become very small. It would become 20, what, 26. All right, there's a drastic change. That's why this bit on the leftmost side is called as MSB. All right, and this one on the left hand side, because this would have least impact on a number, if it gets changed, it's called as LSB, or least significant bit. This is the most significant and this is the least significant. That's the idea why there is a notion of MSB and LSB over there. All right. Also, what happens is, I'll tell you about one more term in terms of computers. You might not need to deal with it directly, but what happens is when you're working with data science, you might not need to deal with it always, but sometimes it may create issues. And you should be aware that something like this exists so that you can fix it and find a solution for it. It is called as endianness. Or I think there should be two in, but endian means there are two kinds of systems. One is little endian and one is big endian. Now, sorry, not big, it should be big. All right. Does anyone know what this means? Little versus big? Any kind of thing you remember? No? All right. See, computer is a system. All right. Now, if you look at this thing, the binary representation of some number, I'm writing it like this, 10100. Let's say I write this. All right. Now, this is the most significant bit and this is the least significant bit. So if I have to put it inside a computer system, what computer can do is it can write it in two ways. All right. It can either write the most significant bit on the left like this, or it can store it in the reverse order also. All right, it can store like this is the most significant bit on the right hand side. So from visual or human perspective, we typically think that the thing on the left hand side is more significant, because since our childhood we see that when we write numbers, we write the value with the more weight on the left hand side. All right, if you look at this number, 2 has more weight, 5 has more weight than 6, and 6 has the least weight. Same way, we look at it like this, the binary, but computer can look at it in any way. It doesn't matter to it. It just need to do the conversions properly. So if it treats this as the most significant bit, all right, it is called as sum endian. I don't remember like which one is little and which one is big, but the way programming or way your computers encode this data or store this data inside themselves is of very big importance. All right, whether they are using little endian or big endian, it's important for other systems to understand. Why? Let's say I save a file on my system which uses, let's say, this notation. All right, it gives the most significant bit on the left hand side, and then I give this same file to you, but your system stores in the opposite way. All right, now if you will read that file or your system will decode the data, it will be all garbage. It will be trash. All right. Now, when storing the data or when storing the file, your system will write along with the information that in what encoding or how your file is stored, so that when you open that same file on another system, that system will get to know that, okay, this system uses little endian, but I use big endian, so I need to do some kind of processing. Or if this system had used little endian which stored the data and I am also using little, I can read it directly. So this is of very much importance to systems. We don't get to know about it most of the times. Even when I am using browser, when I load this website server would send me some data. Now that data would also be encoded in some way, little endian or big endian. Now my system needs to know the way that it is encoded so that it can properly decode it and display everything on my screen. It happens everywhere wherever data is transmitted. All right. So this thing is there. We just don't get to notice it. But in data science, when you will study a bit about NumPy has a notion where you can specify in what kind of endianness you want to store the data, or you can load the data. So it is there. Just remember this term little endian and big endian. I don't remember which one is little and which one is big. It's just a Google search will get to know which one is little, which one is big. It will tell you whether it stores the left MSB or the LSB first. Depending on that, it becomes little or big endian. I think the one which stores the least significant bit at the end is called as little endian, and the one which stores the most significant bit is called as big endian. So it can be either way, but that's fine. That's just a Google search. It's easy to find out. But remembering that this thing exists in the world and it can create issues is important, so that if something like this ever happens in your work, you will know that it might be because of this, and then you will search for a proper solution online. Otherwise, it would be searching like in the dark without any light. All right. So your search would be better. So this is another notion in terms of memory, little endian and big endian. So yeah, this is pretty much about the internals of memory, I think, how storage and all happens. Do you guys want me to recap something, or do you want to note down? I'll just make bullet points or something somewhere, and I can probably show that to you if you want. Oh, okay. Then let's come to our next part, which is also memory, but from a different perspective. All right. So this we saw from a very low level perspective, what happens in memory. All right. But when you buy a computer system, you typically look at memory like this. You buy a phone also. It says like RAM is there, and I think everyone wants to buy a phone with a bigger RAM. I think yes. Then there is a ROM. On phone, it is called as ROM. Like they call it ROM. I don't know why they call it as ROM. It's a wrong term, but I would call it as your permanent or secondary storage. And this thing is called as primary. Initially, I used to get confused why this is called as primary and why this is called as secondary. Secondary means your hard drives, HDDs, your SSDs, basically any kind of storage which is permanent. When I say permanent, permanent means non-volatile. And non-volatile means, I think you guys would remember, that when you turn off your system, the data stored in your hard drive stays as it is. So that's non-volatile. And RAM is your volatile. As soon as your power goes off, it's going to get cleaned up. So when you load it, you have to load all the data again. But why is this called as primary? I used to think like this is better since it doesn't lose power, or it saves the data. So it should be primary and this should be secondary. But this is coming from a different perspective, why they call it as primary and why they call it as secondary. Consider it as something like this. The thing that you go refer to first, or the thing that you would try to use first, is primary. And the thing that you would go in the second step would be secondary, like that. So now when I say primary and secondary from a usage perspective, I'm talking in terms of CPU or processor. All right. So your CPU always refers to your RAM first whenever it is looking for any kind of information or data versus your hard drive and SSD. So that's why it's called as kind of primary. That's my notion of primary now, why it is called as primary. All right. And there are another memories also. I'll just mention the names. Cache. So I have a question for you guys. What do you look for when you buy a phone? Exactly, apart from camera, guys. What do you look at when you buy a phone?
Memory.
Memory, which memory now? Both RAM and your permanent, sorry, or I'll say secondary. Cool. What else do you look? You look at the processor.
Yeah.
Or let's call it as the CPU, correct? Apart from that, do you look at anything? You can say no, because typically we don't look, and camera, yes, but we are not talking about that. So let me know if anything else also you look at. Maybe I don't look at it, I'll start looking at it. But when you buy a desktop or a laptop, all right, a PC, let's say, all right, what do you look at again? Quick guys, same things, RAM, then your hard drive or permanent storage, whether it can be SG or HDD, it depends, but this is permanent storage. Then you look at processor or CPU again, correct? Anything else do you look at? Screen
Graphics
size,
card.
that's not relevant. Yeah, GPU. And again, if you look at graphics, which is called as GPU, so if you're not aware, so there are two things. One is CPU and one is GPU. CPU is central processing unit, GPU is graphics processing unit. And from a data science perspective, this is very important, GPU. All right, it will be very useful for you. So that's a good thing. But again, GPU internally has two things. One is the compute, and GPU also has its own RAM. All right, so that's a different use case completely. So we'll ignore GPU and GPU thing for now. We'll just stick to a PC. In a CPU, do you ever notice what kind of CPU you are getting? i7, i5, or maybe AMD, some variant, Ryzen, etc. Do you look at the specs for these CPUs when you buy a PC? Just tell me from your experience. I think everyone would have bought a laptop or something, correct? Has anyone not bought a laptop till now for themselves? Maybe you delegated it to some of your family members or friends. That's outsourcing that often people do. But uh, do you look at the processor? I do look at it. All right, because that's very important. So I'll just go to, let's say, i5 versus, or let's take the latest things, i7 versus i9. So let's pick some website. I think it won't give you good detail about it. Yeah. So, okay, what I'm looking for is not available here probably. I think we'll need to go to the documentation of Intel itself to find that out. So i7, let's say some variant H1 should show something. Yeah, cache. All right. So let's see if it shows us something. So typically you are looking at a lot of things when you buy a CPU. One is the number of cores, all right. And there is hyper-threading for 8 threads total. This is something else. Then there is clock speed, which is in gigahertz. All right, it says it's from 3.6 to 4.2 gigahertz. That's very nice. And it says 8 MB smart cache. All right. Now this cache is important. All right, this cache is also a kind of memory, which is not talked of more. So if you kind of, if I have to draw a diagram or a chart of memory, so I'll put cache, or it is also called a CPU cache. All right, CPU cache. Then there is your RAM. Then there is your secondary storage or HDD, SDD, etc. All right, and if you look in terms of memory, these are the three primarily which we are concerned about. And why are there so many kinds of memories in a computer system? There is a third one also called as register. I'm not sure if this would confuse you or do what, but if you want to note down these things so that you can read once more, just do that. So these are the four kinds of things which I can remember now. I don't think there is then external kind of things that you put your external hard drives, USBs, etc. That's not at all relevant for us. We'll skip that. Register is something which is inside the CPU or the processor itself. This is part of processor. How should I tell you? So if you have a 4-core CPU, all right, there are 4 CPU inside it. Each CPU will have its own register, all right, set of registers, which is very fast. This is the fastest kind of memory available into your system. I'll tell you why, what we mean when we say fastest. Then there is CPU cache. Cache is something which is, I think, shared by all the CPUs which are present inside the processor chip, all right, but this is a bit less faster than your registers, all right. Then comes your RAM. RAM is external to your CPU completely. You install it outside, which is even slower than your cache. Then comes your hard drive or the secondary storage, which is the slowest of all. All right, cool. So now what happens is your CPU is running at a speed of gigahertz. All right, gigahertz. I don't know what gigahertz converts in terms of number directly, how many zeros are there, but it is a notion of how many operations your CPU can perform in a second. All right, cool. So let's say your CPU is 1 gigahertz. Nowadays, there are CPU from, I think typically I would buy at least 2 gigahertz CPU, and you already saw that variant could have gone to 4.2 gigahertz. But let's say I have 1 gigahertz CPU. Now it can do these many operations inside your system in a single second. Now what happens is this thing comes from something called as clock speed. I don't know if you guys ever have thought of crypto mining, etc. But there is the clock speed is always a hot thing there. All right, for mining perspective, but clock speed roughly means to this, like how many clock cycles or how many operations a thing can do inside a single second. That's clock speed. Just keep that assumption. Now the clock, each of these memories have their own clock speed. CPU has its own clock speed, which is at the peak. Registers, since they are part of the CPU, they work at the same clock speed as the CPU. It would be the same. So when your CPU has to fetch data from a register, it will work at the same speed that your CPU is working. So that's the best you can get. Then you have cache. Cache is slower than your registers, but since it is slower, it is cheaper also. Register would be the most costliest kind of memory that your chip creators can make. It's very costly to make registers. CPU cache is slower in terms of like speed, but you can create more of it on the chip, all right, because it is slower, it costs less, all right, it costs less, but you can put more of it. Then comes your RAM is in, I think, megahertz. It comes in megahertz. I don't know, 800 some your RAM chips are rated in megahertz. What is the frequency of your RAM's clock? All right, so RAM chips also have a speed in megahertz. I don't know what the rough numbers are, but it's in megahertz, and it is slower than your CPU cache also, all right. Then after your RAM comes your HDDs and SDDs, which are like, HDDs are typically 1,000 times slower than your RAM. All right. Now consider something. Let's say your CPU has to read some data. All right. If it goes and reads it from hard drive, it will be very slow. All right. Versus if it reads from RAM, it will be faster. Versus if it is present in cache, it will be faster. If it is already in register, it would be the fastest. All right. So register is something which is used for internal computation. For example, when you say 1 plus 2, so the system, the registers internally load 1, then they load 2, then they add the result and store it inside a register. All right. But once the result is generated, then it needs to get, let's say, stored in your hard drive. So from there, it will go into the RAM, and from RAM, it will get stored in your hard drive or your permanent storage if you have to store it. But this is the rough order. Register is directly used. Then for these 3 levels of memory, your data is loaded and transferred from one into the other so that your CPU can process it. That's the idea of so many levels of memory, because each one is costlier. So typically your cache, CPU cache, is a few MB. How much was this processor showing? It was showing 8 MB smart cache. Earlier, it used to be in KBs. Now your system manufacturers have managed to get it in MB. So this is in MBs. This is in few GBs, let's say 8, 16, 32, 64, or something like that. It is in gigabytes. And your hard drives are also in gigabytes, but they are roughly in TB formats right now. You can easily purchase 1 TB for sure. Most laptops come with 1 TB now, at least. All right. So you can see the sizes are very different. Why? Because if you go and buy a 1 TB hard drive versus let's say an 8 gigabyte RAM, the price or the cost per byte of memory would be much more for RAM compared to hard drive. That's why the amount of memory of each type keeps on getting reduced as you go into faster and faster and faster. This is the notion or the structure of or the memory hierarchy that your system or even your phone would have. Your phone processors would also have all of this, but the thing is your phone manufacturers don't give you that level of information. For example, if I were to buy a PC, I would check what kind of RAM it is. It is DDR3, DDR4, or and even in DDR, what kind of frequency that RAM has. I check at least that, apart from the quantity of RAM. Versus when you look at a phone, they don't manufacture any of these kind of specs about what kind of RAM they are using. I couldn't find it, at least when I tried to search it. So in phone, it's a different domain, but we are talking in terms of computer systems and servers, and all of them will have this kind of notion. And this is your memory hierarchy that's there for your computer systems. Cool. And your CPU is connected to all of them in some way, so that when you say I have to run a piece of code, so let's say I write a piece of code in my system and I save it in my hard drive. Why? Because when I shut down my system, I load it back, that code should be available. All right. Now, if I have to run that piece of code, I have to first load it into RAM. So that code gets loaded into RAM. Once that is loaded, then your CPU will start executing that code. For executing the first, when your CPU says, I want to execute that code, it will be pushed into cache. From cache, it will go, the data will go into register and it will start working. But the most important memory when you are talking in terms of a program is RAM. Remember this thing. This is the most important. You will never hear anyone talking about registers. You will never hear anyone talking about CPU. You will never hear anyone talking about, or rarely hear anyone talking about RAM. But when someone says your program is taking a lot of memory, they are talking about your program is taking a lot of RAM. Because when you run a software, for example, I have this browser Brave installed on my system, and I have this browser Chrome also. Right now, I have opened this Chrome browser. It means this is running on my system. Running means it was saved on my hard drive when I installed the software. My computer loaded that software into RAM, and now it is executing the instructions present inside it so that I can see this view and I can show it to you and I can draw things. Whereas this Brave browser is not running. So where is the content or the installed files stored? They are on hard drive right now. Once I'll click on this icon and I'll launch the browser, it will immediately load it into RAM first, and then it will start executing the instructions that are mentioned or that was written for this browser by the creator of this browser. All right. So as soon as your program starts running, it means you have loaded that into primary memory, or what we call as RAM. And for all future purposes of memory, whenever I say the term memory, we are saying how much RAM that particular thing is using. All right. Even coming back to the very first thing that we talked about today, right to the beginning, which was in terms of int, float, text, etc. Whenever I say the size of these data types, let's say integer takes 1 byte, 2 byte, or some bytes, I am talking that how many bytes it takes when you store the data in your RAM. All right, that's the notion now. So remember now, memory, whenever I say, I'm talking about RAM. Cool. Now tell me if you guys have any kind of questions about any of this stuff. Probably, I'm not sure if you guys already knew, but if you don't know, probably when you buy your next system, you should look at it. How much cache your processor has. I think this laptop which I'm using, it has, I think, 12 MB smart cache. I wanted a 16 one probably, or it has 9. I wanted 12 or 16, but I couldn't find that in my budget. So, but you can notice how much cache it has, because that impacts the performance or the speed of your processor. Even if you have a processor of 4 gigahertz speed, if the cache is less versus in a processor which has more cache, the one with more cache can perform better than the one with lesser cache, even though the speeds might be different. Obviously, speed matters, but this all matters as well. What is the speed of your RAM? What is the speed of your hard drive? Or what is the speed of your SSD? Everything matters when you're working with a computer, because CPU by itself is dependent. It's not independent. It's dependent on all these also. Cool. That's why all these things are important and why people focus on all that. So that's about memory. All right. Now coming back to from where we started. We started with the low level thing. All right. And when we were discussing that low level thing, now remember when I was saying 1 byte, I was talking that byte is stored inside RAM. Cool. It will also be there inside your hard drive, but for all programming or code purposes, we are talking about RAM. Cool. Let's come to this website. I need to close it, but before closing it, I need to show you some things. In typical programming languages like C, C++, Java, you have a notion that each data type is associated to a fixed number of bytes. For example, integer takes 4 bytes in this thing in C++. Cool. Now the range of or the different values that it can represent to store an integer of 4 bytes is this much. This number is huge. All right, it's huge, but it's not so huge. Cool. I think if you guys would have read sometime, because this thing is somewhat popular, and that YouTube initially used to store the number of views inside an integer of size 4 bytes or something like that. But at a point of time, for the first time for a video, the number of views went beyond this number, and then it started showing the value as 0 or negative, something like that happened. All right, why? Because in binary number system, when you add something, binary numbers get added in a different way. So if you add something to a number and that goes out of range, then it moves other way around. It gets into the negative range. All right, so that happens with binary number system, arithmetic, addition and subtraction. So that happened with them. Cool. So this is a known thing that people know that the size of this thing is fixed. Now there are different variants of these types. For example, integer can be 4 bytes, integer can be 8 bytes. But in case of Python doesn't has this notion. That's why I'm telling you about this. In Python, there is no limit on the size of integer. Python automatically will adjust the size. For example, if I was working in C, C++ kind of languages, if I create an shortened, or if you see over here, it has a range of just 32,000 or like 32K. If I wanted to store that salary of 70K inside this, it's not possible to store it. I can store it over here. But let's say I want to store the revenue of a company. Would that fit into this integer? Maybe, maybe not. All right. Maybe they will need a long int for storing that. All right. Or a long int, because the range of these values keep on changing as you increase the number of bytes. So this was 4 bytes. This is 8 bytes. So obviously the range increases. Cool. And this is the notion behind data types in general from a computer and programming languages perspective. Python doesn't use this notion for its data types for integers and floats. It uses a different kind of thing. But when you will come to data science, you will again have to come back to exactly this thing, all right, which Python tries to keep you away from, or which Python tries to hide from you. All right, but later you have to come to it. So that's why I'm explaining all this in so much of detail. When you'll come to data science libraries, they are dependent on all this, because most of the data science libraries are written in C, C++, because that language is faster for this kind of purpose. And hence these limits come into picture over there. Now I can close this, I think. Now let me know if you guys want me to talk about some specific thing, and then probably I'll open your Python interpreter and show you some stuff. But this is the overall low-level stuff I wanted to talk about today. Let's go back. If you want me to go back to some point, let me know. Anything about this thing you're worried about? And is everything clear to you? Anyone is not able to get? We haven't talked Python yet.
Gaurav, just a thought.
Yeah.
Can we check the current cache for our present laptop? Is there any way around to see that?
Yeah, your system processor, whatever processor it has, you can either check online, or you can just go to, I think, properties. Hold on. I remember system configuration. No, not this thing. System information, maybe. I remember I used to see that. So it says OS related details, then it tells me about the physical memory installed is this much, available is this much, and all that stuff. Does it tell you about CPU somewhere? Oh, sorry, my bad. It got hidden behind this Zoom window. I couldn't see it. So you can see that my processor variant is listed over here. It is this. It has 12 logical cores, but actually it has 6 cores. Does it mention anything about cache? But if I just Google this processor variant, it will tell me how much cache it has. Same way you can look up online about your system. It's very easy to do. Yeah. You guys can check it right now on your system. It's interesting to know about your system. So my system is 16 GB RAM with HDD plus STD hybrid thing. And this is the processor, 6 cores, and yeah, with a GPU. I had bought it for a different purpose, but I don't use it for that purpose anymore. So anyways, so what kind of systems do you guys have? Like, do you have IS7 or is anyone running i3 processor? If you guys know which processor is there on your system. No one running i3, i5? No?
Mine is i5.
i5?
Mine is
All right, how old?
Yeah.
How old is it?
How old? How do I see?
No, like when did you buy this? When did you buy the lap? When you bought the lap? So the why I'm asking this thing is, yeah.
Yeah, this is company laptop. I think
Oh, okay,
it's
company
pretty new. Yeah.
But company laptops are typically good. So see guys, one important thing is your system should have a decent amount of RAM. I think at least 8 GB RAM should be there in your system. All right. And I'm not sure when you study data science, what kind of models you would be training, because some models can be trained on CPU also. Long back during my college, I had a desktop with just a CPU and integrated graphics. And I used to train model on it and it used to run entire night. So probably maybe later, not now, you might be interested if you are planning to buy a new laptop at any point of time for your personal usage, go for a laptop with a GPU. All right. And yeah, if you plan to do buy a laptop with a GPU, because probably it will help you with your data science stuff if you go deeper into that. So it would be helpful over there for you guys. Cool. And at least you should have 8 GB of RAM. 16 is good, but depending on your application, for some people even 32 is good. All right, but we are not doing video processing, editing, etc. So 8 to 16 GB is typically good. If I open my task manager right now and I show you the resource utilization, if I go to performance, you can see that 16 GB is there, but it's only using 5.2 as of now. All right, but when you run some heavy applications, it would go till maybe 10, 12 GB or maybe close to what the total installed is, but it depends actually. All right. It also depends on the caching. See, when your system's other resources are slow, your CPU is slow, it will maybe utilize more memory. All right, or maybe utilize more hard drive if your memory is slow. That happens actually. Cool. So there are a lot of considerations, and I want you guys to read about one thing yourself, which is did I write any to-dos last time? Can keep this link with you. So I had done this to do. So you guys have to create an account on GitHub, which you guys have already done. And you guys have to read about all this and install this software Git bash on your system. And you guys can read about swap space. All right. From a code perspective, it's not useful, but from a system perspective, if you are aware of this thing, it's good. From data science perspective, it might not be very useful to you, but from a system perspective, it's useful for as much information you know. There's something called a swap space in computer systems. And once I had created a server on AWS, and whenever I used to run a particular task on it, it used to just crash. The server used to freeze. Then I created some swap space on that server, and the RAM was very low on that server. But after I created swap space, it stopped like freezing for that particular task. So swap space is also something useful. So probably you guys can Google this and read about it. So all this that I put over here, guys, it's your job to read about it. Once you read about it, if you have any doubts, ask me. But it's your job to read about it. Cool. And these are your Jupyter notebook shortcuts. And I think I can remove the usernames from here. We don't need it anymore. So I'll clean that up. And yeah, this is your GitHub repository. Let's come back. Cool. So this is about your computer systems, RAM, etc., etc. Let's come here. So, all right. So, do you ever notice that when you install software, it often says 64-bit versus 32-bit, something like this in your operating system? Even while installing Anaconda, it would have shown two options, 64-bit versus 32-bit. Do you guys notice? No?
Yes.
Yes.
What does that mean? Did you ever search?
No, I think search.
Can
Like,
you do it right
always
now? And
default like 64.
Sorry?
I thought it is a default 64.
It used to be 32 earlier, but now most of them are 64. So its default 64 assumption can be taken. But can you guys search right now on Google and or on any search engine, DuckDuckGo, whatever you use, that what does it mean when they say that 64-bit or 32-bit software? Just search in whatever way you want to search, and then tell me what does it tell you about this thing. Do it right now on your phone or on your system, up to you, but do this right
It
now.
says all about processing power.
No, not processing power, it's something else. Read it carefully. See, you won't get the thing in so quickly. It will take you at least a minute to get there if you don't know. And there are different perspectives of looking at it. So some part can be wrong or right, but not wrong, but many things can be true about this. But take some time to read about it properly. Probably you can
But,
type on chat. Mhm.
so these are type of the architecture which processor possesses. So 64 bits are the newer architecture processor which are quite fast, faster than the older one which used to be 32 bits.
But why? What is this 64 exactly, and what is this 32? Why are these numbers? Why don't they say V1 or generation 1 versus generation 2 or generation 3?
Yeah, they could have
See,
taken
and
16
if
or
you would
32.
notice, it would say 64-bit and 32-bit. Doesn't it say like that? Something like that. X32 and even there's something called as X86 that you typically see. All right, that's the kind of processor series or generation that used to be there. But when I started this thing, I said 64-bit versus 32-bit systems. For example, if I go to my system information again, it would say somewhere X64 based PC. Okay, it says X64. It doesn't say bit or anything. Okay, just take some time, read about it, and probably search with the keyword bit over there. All right, then I think you'll get what I intend to tell or discuss right now. Search exactly 64-bit versus 32-bit systems. Maybe some variant of that. Actually, there are two kinds of things. One is X64 versus X86, that the way they state, and there's 32 versus 64-bit. All right. We'll talk about this right now, this particular thing. What happens is, when you have a RAM, and RAM is divided into what? Bits and bytes. That's the smallest unit would be bit, but bit is not useful mostly in individuals. So typically we talk about bytes. All right, let's say these are bytes. But now your CPU wants to read some data from RAM. All right. Let's say that data is stored somewhere. How would it identify where is it stored, and how will it tell you that get me this particular byte only? What would it do? It would number these bytes and say this is the byte 0, this is 1, this is 2, this is 3, this is 4, and now your system has a lot of bytes. All right, since it has a lot of bytes, it will be a big number. Cool. Because if you say you have 1 GB of RAM, 1 GB is equal to 1024 MP into 1024 KB into 1024 bytes, correct? And this is going to be a big number. All right, this is 2 to the power 30, I guess. All right, so your system will have that many in different bytes with the number. This would be some number. Cool. Now this thing is called as address. Oh, why am I not able to type the address? Okay, I have reached the corner of my drawing. So this thing is called as address of a byte. And addresses are typically written in hexadecimal notation if you will ever get to see them properly. Why? Because writing a big number in decimal number system would be very big. So that's why what they do is, while printing addresses, systems typically print addresses in the form of hexadecimal number system, because hexadecimal number systems representation of binary would be smaller than decimal number systems representation of binary. So that's one use case where hexadecimal number system is used. But anyways, when you typically process some data, all right, CPUs have typically a notion of word size. Word size means how much bytes your processor processes kind of at a point of time. For example, if you want to add two numbers, 1 plus 1, what is the biggest number that it can handle? And word size typically can be either 4 or 8. 4 means 32 bits, 8 means 64 bits. It means a processor with a word size of 32-bit can do operations, or it will load memory from your RAM in chunks of 4 bytes. It will directly load 4 bytes in one shot. Whereas a processor which uses a word of 8 bytes will load 8 bytes of memory in one shot into its word. When I say word size, it directly corresponds to what kind of data size your processor can process, and that is exactly related to the size of your register. So register will be of size, each register will be of size 8 bytes. Each register, so there can be many registers inside your processor, but each will have a size of 8 bytes. And when your processor wants to load some data from your RAM, it will directly load 1 byte into the register in single shot. And now consider, let's say your system or in your programming language, you use integers of 8 bytes. All right. To add two integers of 8 bytes, it will be able to do it in 2 instructions, let's say. All right. I'm giving you hypothetical examples. In actual cases, things might work out. Your processors do a lot of optimizations and it might work out directly also. But it will be able to process granularly in 4 byte chunks. So for this thing, it might need 2 operations. First is on a bigger one, it will be able to do it directly. But what if you want to add integers with 4 bytes, which are 4 in bytes? Obviously, this can do it directly. Even this can do it. Why? Because if you write a binary number 100, if you prepend it with these zeros, does it matter? These are not useless, kind of. All right. So same way, if you put the data of 4 bytes into a word size of 8, it will still be able to do the job. All right. But this is the rough idea when we say 32 and 64-bit. There is another thing in terms of addressing. All right. Addressing means, since the address of each of your memories byte itself, your RAM, is a number. All right. How much RAM you can actually store, how big address you can store, will also depend on what is the word size of your system or how big addresses it can process. So there used to be different kinds of systems earlier. Based on that, this kind of thing is also represented. So it's in 2 terms, but when we say 32 versus 64-bit, we are talking about word size, how big a chunk of memory your system can process in one single shot. This is not relevant or much useful for you guys. I've just given you an idea what this is. It's not relevant from our Python or learning perspective, but the other things that we discussed earlier, which is your RAM and your performance of these memories, that is important. All right. Specifically RAM versus hard HDD, the performance of RAM is superb and HDDs are slow. That's important. Cool. So what kind of memory does your system have apart from RAM? Like, do you have SSD or hard drives on your laptops? Do you guys know? Do you guys notice? If you don't, then start noticing now onwards. All right. So I'll just go to one thing. I wanted to show you something. Let me see. do you guys know about EC2? Who doesn't know about AWS, not EC2? I just want to know so that I can explain to you what this thing is.
Gaurav, I don't know AWS.
Don't know
Yeah, I don't
AWS?
know
All
about
right.
this.
And do you know about this thing? Clouds.
Yeah, I heard of cloud.
Cloud computing.
Yes.
Or cloud, simply. You heard?
Yeah.
All right. Arjun, what about you? Think the lip.
Yes, heard of it.
Sure. You have heard of this thing? Cool. I think okay. So I'll just tell you one simple thing. So I'll first talk about cloud and then what AWS is. AWS is very simple once you understand this thing. So the idea is, like, let's say I was to start my own company. All right. To start my own company, I'll need to purchase hardware to run servers. For example, if I want to build my own website, I'll need to run a server for that. All right. And I'll need to buy hardware. Then once I buy hardware, I'll have to maintain it. I have to maintain the hardware there. I'll have to hire some people who will maintain it. Plus, let's say now I'm serving only 1,000 customers. Tomorrow in future, I start serving 10,000 customers. Then I start serving a million, let's say even more customers. Let's say 10x, then next year, even more, the volume becomes 10x. So I have to keep increasing the capacity of my hardware. All right. And there are special devices that you have to purchase and maintain. So the idea of cloud computing is what they do is these providers take all these resources and they give you these resources as a subscription or as a service, so that you don't have to buy all this, you don't have to purchase the space to keep all this, you don't have to hire people for maintaining it, but instead you have it somewhere, someone else is managing it for you, but they provide you or they allow you to use it directly. That's something which is in rough approximation of what is cloud computing. All right, that's roughly what cloud computing is. Someone is providing you resources for a cost and they are managing everything for it. You can just go and use it without any kind of issues. All right, expectingly, like without any issues. Obviously there can be issues, and they provide you different kinds of services. For example, they will provide you even GPUs, graphical processing units. Also they will provide you storage, they will provide you computation. When I say computation, I mean servers which have CPU and RAM. When I say storage, storage means storage like your hard drive, permanent storage where you can store data permanently. And they provide a lot of other services apart from these, and you can just subscribe to them. And let's say tomorrow you want to shut down your system, or maybe company, you thought like after 1,000 customers it's not growing, you want to stop it. What will you do with the hardware? You'll have to sell it off. All right. In case of cloud computing, you just stop using it and your bill stops coming. It's like as much you use, you pay that much. Simple. All right. It's not like you have to invest in hardware and all of that stuff. And that's in simple terms cloud computing. Now it's a domain and thing in itself, so it's a big thing, but that's roughly an idea of cloud computing. And AWS is just another, not just another, it's the one big cloud provider. So there are a couple. You would have maybe heard of Microsoft Azure. Azure is from Microsoft. Google has its GCP, Google Cloud Platform. Amazon has AWS, which is Amazon Web Services, AWS. And EC2 is what they call their servers for. If you want to rent a server from Amazon, they call it as EC2, Elastic Cloud Compute or something, Elastic Compute, something like that. All right. So if I go and just look at the different kinds of systems that they have, they will give you in detail what are the processors, how much RAM will you get, how many cores are there, and what kind of storage they use. All right. When they tell you storage, they will also tell you whether it uses hard drive or it uses SSD. Even if they tell you it's SSD of what kind, what would be the performance of SSD, what is the read speed of that SSD, what would be the write speed of that SSD. They tell you literally most of it about it. All right. And there are GPU based processors and everything is there. There is a lot of information. So I think gradually, if you guys haven't ever tried this out, probably maybe I won't be taking session on that, but it's you can create a free account over here and there is 1 year free trial, and you can use it and enjoy or learn about Amazon or AWS later, not now. I'm just giving you some idea. So nowadays, that's why your companies are able to build products more easily. Why? Because they can just use these kind of services and and just start building things. All right. And when they need to increase the capacity of the system, they can just go to this cloud provider and increase the capacity on without it doing anything. All right. And if they want to reduce it, they can reduce it as well. Or if they want to close it, it's very easy. So all that problem goes away. And all this is there. So Azure is Microsoft. Even Azure has some free plan for a year or something like that. Yeah, 12 months plan, free services. It's restricted, but you can try out. Even Google has $300 credit or $100 credit, something like that. So if you want to try out or learn about cloud, it's damn easy these days. Like getting a basic understanding of it. You just make a free account, do whatever you want. Not whatever, but yeah, explore things. Make mistakes, learn from your mistakes. That's the best way of doing it. All right, guys. So I think this is pretty much it for today. So what we'll do is from tomorrow, I think I've given you a pretty good overview of this part, internals of computers. From tomorrow, we'll start looking at all of this that we discussed from Python's perspective and from a programming perspective from tomorrow onwards. Cool. So do you guys want this thing, or my handwriting is not that good, but do you guys want this thing, this thing, whatever I've written, or is it fine? You'll anyways get the video. I don't think this thing is very useful, but because mainly what I said is useful.
Yeah, I think we can refer back to the video.
All right, cool then. So let me know, guys, if you have any doubts. Then I think we'll close today's session probably, and tomorrow we'll start with some interpreter. We'll do things over here inside this black terminal. Cool. Any questions, anything you want to ask, maybe outside of this, that's fine. I will be happy to answer anything about work or how things work out or something. I'll be happy to answer. Yeah.
Like why people hesitate to buy AMD?
Sorry, I didn't get.
Why do people hesitate to buy AMD processor?
Why do people? Sorry, I'm
Hesitate.
sorry. I'm
like people don't
why do
buy
people
AMD.
hesitate to buy AMD processors?
Yeah.
Even I hesitate to buy. There are many reasons. See, whenever you don't know about something, when is a person afraid of something? When they don't know about it. Same way, if someone hasn't used AMD processors and they don't know, they'll just search online and they'll find both positive and negative things. But at the end, a person gets confused, and then they realize, like, everyone around me is using Intel. I have been using Intel. I should stick to it. That's it. But otherwise, AMD processors, I've heard they have some heating issues. They heat more or they generate more heat, but they are cheaper. I think now the heating issues have gone. And another thing is support. Support is very important thing. Remember, for everything, whenever you buy anything, all right, support is something which is very important. For example, you buy a laptop. If it has some issues at certain point of time, if you're not able to take it to a store, or maybe no one visits your home there's no service available for it. It's a problem. All right, how will you get it fixed? Or if the parts are not available in the market, that's a problem. So typically support or service is also of very much importance, and that's there for softwares also. So I think initial support, so initially when I told you about support, I was talking about physical or hardware kind of support for those kind of things. When we talk about processors, let's say someone builds a software that runs on some certain operating systems. Now processors themselves have a different architecture, and your softwares have to be sometimes built for those specific architectures. So since Intel has been there for a long time, and in the retail segment, I think in the server segment, AMD was still there, or I think in some segment AMD was there since long, but that also matters. So probably I think support for AMD kind of chips might not have been earlier. I didn't explore them, but now people are using AMD processors and it's working fine. So there's not much issues these days, but it's still the same thing. I also bought an Intel chip. There is that thing, but yeah, with this is a good question. Remember, there is something called a software support also. All right. So why would someone go to Amazon or Google or this thing, Microsoft Azure? also depends on what kind of support they're providing. Let's say you buy a machine and you use their some service and there's an issue, you drop them a mail, you go to support and contact them, and they don't come back to you quickly, or they don't answer you quickly. So that is also important when selecting services, software services, and even softwares also. For example, if you look at certain softwares like let's say Ubuntu, all right, or even Python or any kind of software, they come with a kind of support that till when will they publish updates, or till when will they fix the bugs in the software. So all that has to be considered as well. So support is also one big thing even for softwares. Because if I have to install a library in Python, I would try to install that library which has good support. All right. What if the developers who are building that library, they all of a sudden decide like we don't have time to work on it. So if there is a bug, it will stay as it is forever. Probably you fix it yourself, but that would be a long time. So support is something very important, but yeah, that's the thing. And AMD and Intel processors vary in terms of their architecture. Also, there are two kind of architectures: RISC versus CISC. RISC means reduced instruction set. CISC means complex instruction set. All right. So I won't go over there, but these are also some things on which processors vary. I think AMD uses RISC architecture, Intel uses CISC, complex instruction set, and AMD uses reduced instruction set, or it's a simple one. Yeah. Anything else? No. Okay, guys. Then good night, and let's meet tomorrow. Cool. Just if possible, revise this thing before the session tomorrow, or maybe you can do that over the weekend or next week in the weekdays also. Because from tomorrow we'll talk in from a Python perspective, and tomorrow is going to be interesting somehow. Yeah, even better than this maybe. Cool. Okay, guys. Bye. Thank you.